هذا اللي بيتكلم.
We are ready to start the first session. We have been asked for 2-3 minutes just to adjust the logistics and the technology, so thank you for your understanding.
Bismillahirrahmanirrahim. Comme nous avons la traduction simultanée, on a le choix d'utiliser les 3 langues, le français, l'arabe et l'anglais. Et nous commençons cette première session par l'intervention de M. Boulan Edogan concernant les nouvelles approches thérapeutiques pour les soins personnalisés contre le cancer. Alors, je donne la parole à M. Boulan. Il est où? Je vous en prie. Monsieur Boulan?
You have
Oui,
the floor.
c'est juste à côté. Monsieur Boulan est des États-Unis.
Mr. Boulan is Associate Professor and Director of Medical Physics at the University of Chicago, Islamic School of Medicine, USA. Thank you. You have the floor.
Test. Okay.
Good morning, everyone. Distinguished fellows and distinguished guests, thank you so much for the organizer for inviting me and listening me today with my presentation. It's about novel theranostic approaches for personalized cancer care. So, little fun facts. As we all know that, we call this theranostic. However, we have been using this as theranostic as well. So it is supposed to be a combination of 2 words in Greek, therapy and diagnosis. However, when we use as a theranostic, you cannot really see my, most likely, right there. It means by itself does not refer to therapy at all. In mythology, it means god of war. In biblical Greek, it means the hunt. And today, it is actually a Greek island, Santorini, in Italy. So linguists actually looked into this word, how this happened, theranostic, because it really does not mean what we actually use it for. And then they suggested that maybe we should use it as a theranostic. At least the gnosis in Greek means the knowledge. And the knowledge, knowing about the tumor, helps us to find the tumor and kill it. So, you can still use it as a theranostic. However, proper use, it seems like to be theranostic. So, after this fun fact, let's go to a real deal. Needless to say, cancer is one of the leading causes of death and morbidity. And it has a very complex pathophysiology. As such, we have quite a bit of different therapies today that we use to treat cancer. However, none of these things or none of these approaches has the specificity that we need, that we can personalize the treatment. Cytotoxicity is really a big limitation, that how much of the dose that we can give to these patients, and therapy resistance, especially if you use multiple drugs, multiple modes of therapy, it actually limits our fight against the cancer. So we desperately need precision medicine. However, the precision medicine it was a dream 10 years ago, and then it is still continue to be dream. However, we are starting to opening the doors of the personalized therapy. As you can see, there's at least 7 to 10 different modes of the therapy, cancer therapy. So it is in the interest of time, we cannot talk all about them. So we are going to be talking only about the radiation therapy and then how we can personalize the radiation therapy. Okay, first of all, the first pillars of precision medicine is the imaging. Imaging not only to identify or localize, also to find about the other attributes of the therapy or the cancer is really important. What are these attributes? Where there are the most burdens are happening, how aggressive they are, right? These are very important for us to be able to treat these cancers. So imaging is a mode, however, it's also lack of specificity, resolution, and how early is early. And we find out that the early does not mean early unless we find them when it is down to one single cancer cell. Because if you have only one cancer cell, it can turn anytime to be a growing or, like the growing tumor that you will be suffering from it. Based on the sensitivity of the different imaging technologies, as we can see that, we actually have to use so many different technologies to be able to go from anatomy all the way to the biology of the radiation, where we really need all the attributes. And so today, where we use the X-rays and then the CTs in the treatment room that we are going to be talking about, really stays or really not enough or able to gives us the precision medicine. As such, as we move a little higher to physiology and metabolism of the cancer, where we have the MRIs and then nuclear medicine and then PET imaging, we get to start finding about how we can personalize the cancer or the radiation or the treatment for the patients. So we have to really look into areas where we can get, how we can personalize the PET and then MRI so that we can actually look into the molecular metabolism and then biochemistry of the cancer. So we can personalize it. Okay, so this is actually a CT, cone beam CT, most of the 90% of the treatment machines today in the world has only cone beam CT in the room. But then you go to the CT, this is the diagnostic CT. As you can see, you actually start differentiating the tissue from the bone and a little bit of the tissue, however, not much as, MRI. And then this is a T1 imaging, as you can start seeing that in the brain, you start seeing the gray matter and then white matter. So, you start differentiating some of the tissues as the MRI is really good for the tissue. So when you go to the PET scan, where you start appreciating the biology. And, anyone can tell why some of the areas in the brain are red and then some of them are actually the color wash that you see. It's because your brain is functioning, okay? And then the PET imaging has here the oxyglucose. And then the functioning something in your brain, the more you use the sugar, the more your brain is working, actually it's going to get like more red. More red areas in that brain actually using more sugar. It's working harder. As you can start seeing that, like you actually imaging it. Okay, so how about the tumor? So we are seeing on top a CT image. As you can see, like this patient has a glioblastoma, a tumor, a deadly tumor. For instance, in the CT, you cannot see it. However, in T2 weighted image, MR image, you start seeing some stuff in there, right? But like you don't really know where it is until you get a PET image. Okay, right here. Look at how beautiful it is. That red area is again what we call is, like more deoxyglucose, more sugar consumption are happening. So tumors are growing actively. So, they eat sugar to grow. As such, like you start seeing that, like the highlighting as the active metabolism. So you start actually imaging it. So based on these, we start having these combined machines, PET MRI or PET CT, so that we can actually put the beauty of two imaging modalities together. CT gives you the beautiful anatomy. As you can see, PET, you don't see any anatomy. And then we really need the anatomy to localize and treat cancer, right? So we need both of them. So that's what we actually developed, and then today is widely used. Okay, so in a nutshell, the current modalities are not specific enough to differentiate tumor from surrounding tissues. We need to follow the metabolism or biochemistry of, and then where that's available generally in the MR and then the PET region. Resolution, however, is not optimal. You cannot really go down to one cell level or, like smaller areas. You cannot, for instance, with the PET, you cannot see any, any tumor less than 0.6 centimeter, versus in the CT, you can see tumors down to 0.1 centimeter. So again, considering even one mutated cell can cause a cancer, we still have long way to go to be able to see the tumor and then target the tumor. So the other issue with the tumor moves, especially in the abdomen, right? So this is an MRI image. As you can see here, the green is where the tumor, and red is where we're going to treat this patient based on if we don't have anything, knowledge about it, right? And then in the treatment room, unfortunately today, we don't have this kind of imaging where we can see the tumor and then target the tumor. Unfortunately, as such, we are putting much larger margins, and then we treat all these areas that tumor is moving. So that is actually cytotoxicity comes, or the toxicity with the treatment comes, and then side effects of the treatment comes. So we have to really focus the treatment to the tumor and then treat it if we want to really treat and then personalize the treatment. Okay, so again, today this is a modern treatment machines. Actually, this is an image from our center, and then it's considered modern. However, this machine can only have an image this. As you can see, this is again very bad image, and then you cannot really see the tumor in here. And then as such, what we do is we put some fiducials in there where the tumor is, and then try to target these fiducials because we can see them. Okay? As such, like this is actually what's happening in the treatment room. It's a fun fact. However, unless you image and image and then image again, you're not going to be able to really see the tumor and then target the tumor. And then unfortunately, some innocent organs or tissues around the tumor are going to get hit. And you don't want to do that, because actually radiation can cause cancers, secondary cancers, and then it can even cause a hole if you're treating a very specific area like close to stomach or like your bowel or bladder. So you want to really avoid it. As such, this is the first project that I worked on. The reason that I worked on, because I was explaining to you that in the radiation room, CT does not have the specificity of the tumor. PET has it, and then PET-CT fusion gives us a beautiful thing. So the question was for me, can I get the same image that we can get PET with the CT, right? So that will solve quite a bit of the problem because PET is not available widely, and as such, it's very difficult. So, anybody knows about the PET technology, what it requires? Radioisotopes, right? And then that needs a cyclotron. So I'm not sure if we have a cyclotron in Morocco, for instance. We do, right? So there are countries that, they don't have it, and then its production is very difficult, right? So it takes 6 hours, the half-life decay. So within the 6 hours you have to use it. So very much difficult to use the PET imaging. So this shows, how the PET works in a nutshell. We have a positron emission emitting radionuclides, unstable, and then decay with a beta decay, and gives us a positron, and then it annihilates. Let's go back. It annihilates, and then you get like 2 511 keV photons, and then you basically detect them, and then the origination of that annihilation is happening is where the tumor is. So how you basically go ahead and then find out where it is happening, basically, or how you actually trace the tumor with something like that. We actually attach a radio tracer. We call it, in this case, for instance, widely used radio tracer is sugar, based on the explanation that I have given to you, right? The tumor use sugar as such, we are going to be using it. How long I have? The time? Is there any time? Okay. The other one is PSMA. Is a prostate-specific membrane antigen. And then, it is really expressed in the prostate tumors. As such, we can actually detect the prostate tumors. Okay. So all these things on the left-hand side, it's stated with left, is the disadvantages of the PET. However, if we can do similar things with the CT, as you can see, on the left, all the advantage of the CT, if you can develop a CT contrast agents that will give you the specificity of the PET imaging. It is, the longer blood retention, easier to synthesize. You don't need a cyclotron, stable and long shelf life. So if you produce one of these things, then you can just keep it for 2 years and then in the shelf, and then you can use it. So you don't need to have all these logistics, right? Non-radioactive, EPR effect uses to get into the tumor, and then also tumor-specific targeting. The toxicity is still, is investigated, but, you can directly inject it and then to avoid the toxicity to the tumor. So to be able to develop something PET-like, I had to learn about, how the FDG works, how it gets into the tumor, and then this is the mechanism. First of all, there's an elevated metabolism in tumor cells. We call it Warburg effect. And FDG preferentially taken up through the GLUT protein in the cell membrane. And this is the sugar gets into the GLUT. GLUT takes it into the tumor inside the cell. And then, there is a mechanism called hexakinase 6-phosphorylates FDG into the FDG 6-phosphorylates. And after this happens, this actually ensures that, this molecule stays in the cell so that we can image it. Okay, sorry. Okay, so this is the mechanism. So, we basically has to use a similar mechanism, and then as you can see, the sugar metabolism is a long chart. And then I'm not going to get into this, but today scientists actually looking at the sugar metabolism of the normal cells and cancer cells, and then trying to actually turn down the cancer, some of these pathways, so that they can actually reduce the consumption of the sugars by the cancer cells, so that they can actually treat the cancer by this way. Okay, so when it comes to doing a similar thing, that we find out actually a way of connecting the sugar to the nanoparticles or the nanoparticles to the sugar, and then patented it in 2015. And then we actually demonstrated that this mechanism can be repeated. However, you have to be very specific because unless you go to specific carbon atom and then attach your nanoparticle, it's not going to work. And then that is the 2 carbon position. Okay, so after we did that, we have demonstrated through the tunneling electron microscope imaging that, we actually, our nanoparticles gets into the cell membrane, and in vitro experiments has been demonstrated that, exactly what we are telling you right now, nanoparticles by itself, when you inject to the animals or the in vitro dishes, Petri dishes, it can not really show as much or taken up by the cells as such, it does not really concentrate in the cell, and then you don't see it as red. So all the way bottom, when you attach the 2 carbon position, as you can see, that it is taken by the tumor cells. And then if you do not attach the 2 carbon position, 1 carbon position, then you're not uptaken again as much, showing that, you have to be very specific. And then this is, one of our animal, as you can see, the tumor is concentrated in the, the nanoparticles showing red, almost black in the tumor. And then this is actually, you are not able to see it. The resolution of the is not that good. But then, you will be seeing, this is the MRI, how the tumor will work. This is a CT, I can definitely see it over there, but not there. I'm sorry, you cannot see it. But when you do the CT imaging with the nanoparticles, you can definitely see the tumor, and then you can target it. Okay. So this is actually 3D rendering. You can see much better. This is without the nanoparticles. As you can see on the left, there is no tumor. However, if you inject the nanoparticle with the deoxyglucose, as you can see, on the right-hand side, there is a tumor, showing up as clear as bone. Okay. And you can also use nanoparticles, these nanogolds, as radiosensitizer. When you treat these with the 6 ME photons that we are treating cancer patients, as you can see, the survival fraction is decreasing quite a bit. Okay, so currently we are actually looking is how we can enhance the brachytherapy by using these. As you can see, our results shows that we can increase the dose to the prostate and then reduce the dose to the urethra and rectum, which is actually, where the side effects of the radiation treatment comes if we can use the nanoparticles. And then how we can specialize. This is a MR image of the tumor. And, as you can see, you cannot really specify where the tumor is. However, that's because of that, we are treating the whole prostate gland, as if it's the whole tumor. However, using some PSMA targeting, which is right now in the behind, I'm not sure why, you cannot see that. But, you can see that, they localize the tumor, and then if you localize part of the tumor, then you can actually deliver more nanoparticles in those areas through the needles. As such, you can do a personalized treatment. Okay. Right here, as you can see, we deliver much more doses in there by using these localized nanoparticles. Okay. This is some toxicity information. In animals, we are still working the toxicity issues, as I mentioned, is still being worked out. But currently, I think, the systemic injection of the nanoparticles is toxic. However, you can directly inject to the tumor or use through the way that we are doing with the needles through the brachytherapy, and then you can achieve actually reduce the nanotoxicity. So this is a second project that we are working, and then this is last year we got a $2.5 million from NIH to do this project. So here what we are doing is actually individualizing the treatment for prostate cancer, as I was telling you. So I'm not going to get the some of the facts. So this shows a radiation treatment, a radiation treatment with X-rays. And as you can see, there is quite a bit of side effects of the radiation therapy of any type. So our goal is to reduce all these, like the side effects of the radiation therapy. How we can do that? One is basically there is currently an effort, and then there's two companies, they develop MR-guided linear accelerator. So with this linear accelerator, we can actually definitely see the tumor with the MRI and target them on real time, okay? However, still, it lacks the specificity of seeing the tumor, like the, unless you develop a tracer to see it better. So what we are looking at, radiosensitizers, and then theragnostic study. So we are gonna first attach, like the tracers to the nanoparticles, and then use that, and then also look at that nanoparticle new contrast agent, whether it's going to be working as a radiosensitizer. What we mean by the radiosensitizer, increase the amount of the energy deposited, like from the nanoparticles to the cells or to tumors. And then that is actually through the reactive oxygen species, where you can create through the nanoparticles, which is the high Z materials, like the through the radiolysis of the water. Okay, so coming here, like I'm just gonna interest of the time, pass these some information. Okay, so this is actually, like what we are looking at it. You can see a PSMA targeted to the tumor, and then there is two tumor types on the same animal here. On the right-hand side, where you see with the red, is a PC3 PIP, which is a PSMA positive tumor cells, and then on the left, which is the negative one.